Hi, welcome back to Easy Maths with Dr. Nasir, your path to math confidence. In today's lecture, we will see existence and uniqueness theorem for first order initial value problems and related exercises. Existence and uniqueness theorem. Suppose x naught, y naught belong to I cross j, where I and j are some intervals of r, and f from I cross j to r is continuous. Then the initial value problem dy by dx is equal to f of xy. Y at x naught is equal to y naught has a solution y defined on I. Further, if partial f of partial y is continuous on I cross j, then the initial value problem 1 per 1 has a unique solution y defined on I. We'll see an exercise. Determine at least two solutions of the following initial value problem. dy by dx is equal to 3y exponent 2 by 3. Also y at 0 is equal to 0. We'll see solution. In this exercise, f of xy is equal to 3y exponent 2 by 3, which is continuous on r square. So the initial value problem 1 by 2 has a solution on r. However, partial f of partial y of xy is equal to partial y of 3y exponent 2 by 3, which is equal to 2 over y cube root, is not continuous on r square. Clearly, y1 of x is equal to 0 and y2 of x is equal to x cube are two solutions of the initial value problem 1.2 on R. We'll see another exercise. Determine at least two solutions of the following initial value problem. X dy by dx is equal to 2y, y at 0 is equal to 0. We'll see solution. Here f of fy is equal to 2y over x, which is continuous on R other than 0 across R. So the initial value problem 1.3 has a solution on R other than 0. For the partial f of partial y of xy is equal to partial y of 2y over x, which is equal to 2 over x, is also continuous on R other than 0 cross R. So solution of the initial value problem 1 by 3 is unique on R other than 0. However, y of x equal to c s square, where c belongs to R, is a one parameter family of solutions of the initial value problem 1 by 3 on R. We'll see another exercise. Determine a region of the two-dimensional space R square for which the ODE dy by dx is equal to y exponent 2 by 3 has a unique solution passing through a point x naught y naught in the region. We'll see solution. Here f of fi is equal to y exponent 2 by 3, which is continuous on R square. So the initial value problem 1.4 has a solution on R. For the partial type of partial y of xy is equal to partial y of y exponent 2 by 3, which is equal to 2 over 3 y cube root, is also continuous on R cross R other than 0. So solution of the initial value problem 1.4 is unique on R. If x naught y naught belong to R cross minus 50 to 0 open interval, then the required region is R cross minus 50 to 0 open interval. If x naught y naught belong to R cross 0 to plus 20, then required region is R cross 0 to plus 20 open interval. We'll see another exercise. Determine region of two-dimensional space R square for which the ODE dy by dx is equal to xy square root. Have a unique solution passing through a point x naught y naught in the region. We'll see solution. Here f of xy is equal to fy square root, which is continuous on minus 20 0 close interval cross minus 20 0 close interval union 0 infinity close interval cross 0 infinity close interval. So the initial value problem 1.5 has a solution on R. For the partial type of partial y of xy is equal to partial y of xy square root, which is equal to 1 or 2 x over y square root, is continuous on minus 20 0 closed interval cross minus infinity 0 open interval union 0 to plus infinity closed interval cross 0 to plus infinity open interval. So solution of the initial value problem 1.5 is unique on R. If x naught y naught belong to minus infinity 0 closed interval cross minus infinity to 0 open interval, then the required region is minus infinity to 0 closed interval cross minus infinity to 0 open interval. If x naught y naught belong to 0 to plus infinity closed interval cross 0 to plus infinity open interval, then the required region is 0 to plus infinity closed interval cross 0 to plus infinity open interval. I'll see another exercise. Determine a region of two-dimensional space R square for which the ODE x divided by dx is equal to y have a unique solution passing through a point x naught y naught in the region. Well, see solution where f of f is equal to y over x, which is continuous on R other than 0 cross R. For the initial value for 1.6 has a solution on R other than 0. For the partial type of partial y of xy is equal to partial y of y over x, which is equal to 1 over x, is continuous on R other than 0 cross R. So solution of the initial value from 1.6 is unique on R other than 0. If x naught y naught belong to minus infinity 0 open interval cross R, then the required region is minus infinity to 0 open interval cross R. If x naught y naught belong to 0 to plus infinity cross R, then the required region is 0 to plus infinity cross R. We'll see another exercise. Determine a region of the two-dimensional space R square for which the ODE dy by dx is equal to x plus y have a unique solution passing through a point x naught y naught in the region. Well, see solution where f of f is equal to x plus y, which is continuous on R square. So the initial value problem 1.7 has a solution on R. For the partial type of partial y is equal to partial y of x plus y, which is equal to 1, is continuous on R square. So solution of the initial value problem 1.7 is unique on R. Further, the required region is R square. Well, see another exercise. Determine a region of two-dimensional space R square for which the ODE 4 minus y square dy by dx is equal to x square have a unique solution passing through a point x naught y naught in the region. Well, see solution where f of f is equal to x square over 4 minus y square, which is continuous on R cross R other than minus 2, 2. For the initial value problem 1.8 has a solution on R, where the partial type of partial y is equal to partial y of x square over 4 minus y square, which is equal to 2x square y over 4 minus y square square is continuous on R cross R other than minus 2, 2. So the initial value problem 1.8 has a unique solution on R. If x naught y naught belong to R cross minus infinity to minus 2 open interval, then the required region is R cross 150 to minus 2. If x naught y naught belong to R cross minus 2 to 2 open interval, then the required region is R cross minus 2 to 2 open interval. If x naught y naught belong to R cross 2 to plus infinity, then the required region is R cross 2 to plus infinity. We'll see another exercise. Determine region of the two-dimensional space R square for which the ODE 1 plus y cube dy by dx is equal to x square have a unique solution passing through a point x naught y naught in the region. Well, see solution here f of xy is equal to x square over 1 plus y cube, which is continuous on R cross R other than minus 1. So the initial value problem 1.9 has a solution on R. Further, partial type of partial y is equal to partial y of x square over 1 plus y cube, which is equal to minus 3x square y square over 1 plus y cube square is continuous on R cross R other than minus 1. So the initial value problem 1.9 has a unique solution on R. If x naught y naught belong to R cross minus infinity to minus 1 open interval, then the required region is R cross minus infinity to minus 1. If x naught y naught belong to R cross minus 1 to plus infinity open interval, then the required region is R cross minus 1 to plus infinity. We'll see another exercise. Determine region of two-dimensional space R square for which the ODE x square plus y square dy by dx is equal to y square have a unique solution passing through a point x naught y naught in the region. Well, see solution. Here f of fy is equal to y square over x square plus y square, which is continuous on R other than 0 cross R union 0 cross R other than 0. So the initial value problem 1/10 has a solution on R. Further, partial type of partial y is equal to partial y of y square over x square plus y square, which is equal to 2 square y over s square plus y square is continuous on r other than 0 cross r union 0 cross r other than 0. So the initial value problem 1 button has a unique solution on r. If x naught y naught belong to minus infinity to 0 open top cross r, then the required region is minus infinity to 0 cross r. If x naught y naught belong to 0 to plus infinity cross r, then the required region is 0 to plus infinity cross r. If x naught y naught belong to 0 cross minus infinity to 0 open double, then the required region is 0 cross minus infinity to 0 open double. If x naught y naught belong to 0 cross 0 to plus infinity open double, then the required region is 0 cross 0 to plus infinity open double. Well, see another exercise. Determine region of two-dimensional space R square for which the ODE y minus x dy by dx is equal to y plus x have a unique solution passing through a point x naught y naught in the region. Well, see solution. Here f of fi is equal to y plus x over y minus x, which is continuous on x phi such that x phi belongs to R square x naught equal to y. So the initial value from 1.11 has a solution y on x such that x belongs to R x naught is equal to y of x. For the partial f of partial y is equal to partial of partial y of y plus x over y minus x, which is equal to minus 2x over y minus x square. Is continuous on x phi such that x phi belongs to R square x naught is equal to y. So the initial value problem 1.11 has a unique solution y on x such that x belongs to R x naught equal to y of x. If x naught is less than y naught, then the required region is x phi such that x phi belongs to R square x is less than y. If x naught is greater than y naught, then the required region is x phi such that x phi belongs to R square x is greater than y. Well, in the next lecture, we will see some more exercises. Don't forget to share, like, and subscribe Easy Maths with Dr. Nasir, your path to math confidence.